Welcome to section 8.3, which is on volumes. Uh, there's going to be several different, hopefully short videos that kind of explain different methods of finding volume of 3D objects using calculus. The basic idea, though, is sketched out here for the majority of our methods, which is we're going to do this by finding cross-section areas and then adding up all of our cross sections. And since we're accumulating all of the cross sections, that means we're doing an integral of the cross sections areas. So first idea is just get a picture so we can visualize what's happening. So we'll sketch the solid and we'll sketch its cross section. Then we need to figure out the area of that cross section, figure out what our upper and lower bounds will be, and then integrate so that we add up all the cross section areas, and that will give us the volume. There are several different methods involved in this. And so what we're going to be looking at in these videos are solids of revolution. These are where we take a function and rotate it around a line, around an axis, and we're going to focus first on rotating around axes. And the easiest ones to deal with are if we take a function and rotate it around the x-axis. And so we're actually taking this curve and rotating it around into 3 dimensions. And to get an idea of what that looks like, let's say here is the region I want to rotate around an x-axis. And I'm actually taking it and pulling it around, such as this, to get the shape, till we get back where we started. And what will happen is, as we do it, it makes a solid. So we can see now, as it's rotating around, it is creating a solid shape. And in order to get a better idea of what that looks like, we can see as we turn this around, yes, now it's now in 3 dimensions. We can see how it's curved. More importantly for us, we can see that its cross sections are circles as we look at it from the end. And that helps us get an idea then that anytime we rotate a function, we're going to be getting circles as cross sections. And so with this, and this is where we have to kind of get some practice, is if I start rotating this function around, the way I tend to draw them is I tend to do a mirror image first, something like this. And then because it's revolution, I do know that I'm making circles for cross sections. Thank goodness for computer programs that help me visualize that it's kind of a doorknob shape. But then, as I said, what we care about is that our cross sections are circles. And in this case, the center of my circle is the x-axis. It's what I'm rotating around. Well, to find the area of a circle, I need to know its radius. Well, the radius is actually determined by the height of the function. So I can see here that no matter where I were to put a cross-section, the radius of it is where the height of the function is for that x value. So I need that radius, which means area is pi times the radius squared, so it's pi times the function squared. So my area is pi, and we said that here my radius r is equal to the y value, which is 2 plus x cosine x. So my area is pi times 2 plus x cosine x squared. So that gives me the area of just one cross-section, but then I need to accumulate all of the cross-sections. And so that means I'm doing an integral of the cross-sectional's area. And then I just need to worry about what are my bounds. Well, I can see I've got all x's here, so I really care about what are the x's between. We're actually told the x's are from -2 to 2. And when I calculate this, I get an integral of 52.429. And then there are no units, so I don't need to worry about units, but if there were, they'd be something cubed. The nice thing is because we always get circles for cross sections, if we rotate around the x-axis, this is what's called a disk method. The way we find volume is always done this way. I personally do not memorize this. I always think of it in terms of how I went through it here and saying, well, my cross section makes a circle. I know how to find the area of a circle. So once I know that the radius is the function, the area of the cross section would be pi times the radius squared, and then accumulate all my cross sections to get my volume.